Hey everyone, so I'm Danny. I'm a PMC member for Beam and staff engineer at Google. And I added the vLLM support to Beam initially, and folks have improved on it since. So I'm going to talk about how this kind of works. So the first few minutes are going to be the kind of refresher from some of the previous talks. So if you were in the last talk, you might have some overlap, but then we'll get to new stuff about 5 minutes in. So to start off, just like high-level level setting, when we think about the machine learning lifecycle, kind of the traditional lifecycle, these are the stages we think of. So we think of like you get your data, you do some validation, you pre-process it, you do some training, you validate your model, and then you eventually deploy your model for inference. And Beam is generally good at a good chunk of these things. I would say data ingestion, like it doesn't have data at rest, so it shouldn't be used for that. And then training in special cases only if you're doing online training, but the rest Beam kind of fits in well. And today I'm specifically going to be talking about those last two steps, model validation and deployment, both of which require serving your model for inference. So again, this is level setting. If you were in the last presentation, you can tune out for the next 3 minutes and come back. When we think about distributed inference, there's a bunch of challenges associated with them. You need to be able to load your model efficiently, and memory management is especially important there. And I'll dig in on that in depth when we talk about vLLM because it's particularly relevant. Likewise, batching is really relevant. You need to be able to dynamically batch your data to kind of hit the needs of your model, depending on what it can handle and kind of the target batch sizes that you want. You want to be able to update your model on the fly, and you want to be able to use multiple models in your pipeline for A/B patterns or just multi-model pipelines in general. Fortunately, Beam handles all of this out of the box with the RunInference transform. It'll handle efficiently loading your model, batching, updates, kind of everything I just said. And you just need to provide configuration to tell Beam how to find your model and how to load it. So in practice, this is what the RunInference transform looks like. So you've got some config. In this case, we're using the PyTorch model handler, which is loading a model from a PyTorch format. You can feed that into a pipeline and run it. You shouldn't really need any particularly specialized knowledge to do this. You just need to know how your particular model works. And I'll give an example in a minute. I'll switch to a demo here. Would you mind switching over to the demo screen for me? Cool, there we go. I've already got dependencies kind of pre-installed here, so we can just run through what RunInference looks like in practice. So obviously you've got all of your imports, and this is what's going to do kind of the bulk of the work for this particular pipeline. So you can define a model handler. In this case, we're going to use one from Hugging Face, which has a bunch of pre-trained models. We'll use just kind of a small model that can fit into Colab memory so that we don't here. Once our dependency step finishes, this should run. And for this, it's just kind of a toy example. We'll do a couple translation tasks. We'll format the output. And then we can run this pipeline. And that is all of the code that you need to do a scalable sentence translation task. So you'd probably switch out the source and the sink in practice, but that's kind of all that is necessary. You can see it's going ahead and it's downloading the model, and it's spitting out the outputs. Could you switch back to the slides, please? That's kind of a quick overview of how this works. And again, if you've been in this room for a while, some of that might be refresher, but come back now. Next I'm going to talk about vLLM. And that's kind of the focus on this talk is how vLLM works together with Beam to make serving not just easy, but efficient. So what is vLLM? vLLM is an open source library which is used for serving large language models. And it's specifically optimized for large language models. You can't use it to serve kind of any random model. It's specifically for LLMs. And there's a couple efficiency gains that you get as a result of that. Two that are particularly useful are continuous batching and page detention. Page detention is just a way of optimizing your memory usage. So it allows you to take larger models and serve them on smaller machines than you would be able to otherwise. But continuous batching is maybe more interesting to talk about for our particular use case. So when we think about batching, traditionally when you've got a machine learning framework, you want to have batching so that you can do some of these like tensor parallel operations more efficiently. The kind of TLDR is it's faster to do 4 things at once instead of doing them in sequence. And most models are optimized for these kinds of operations. There's some problems here though. So what if some records take longer than others? So you can imagine I have 4 inferences, and depending on my model architecture, it might take me a really long time to finish a specific inference. This is bad for a couple of reasons. One, your model is not actually operating on 4 things at once anymore. It's operating on 1 thing. And in some cases, this might be the majority of the time that it's running. So it's inefficient for your model process. The other downside is that you don't get your result back as quickly, so you can't do other things. You're just kind of sitting there waiting for the model to get back to you. And that's even more wasted compute as well. So it's very inefficient, and it adds latency to your pipeline or whatever task you're running. So how does vLLM, taking a step back. So LLMs see this in particular. So LLMs basically perform a sequence of inferences. So when you think about a single LLM inference, instead of it just being one giant inference, basically the way it's broken down is it predicts the next token, then it predicts the next token, then it predicts the next token. So this is expensive if you've got a really long sentence or a really long thing that it's predicting relative to your input. And so this is pretty common if you're doing bulk inference with large language models, where you might have like in this example, you might have a really short response, and that gets paired with a long response, and you just kind of sit there and wait. So the way vLLM works around this is instead of batching at the entire input level, it batches at the token level. So what this means is that instead of batching the whole response together, it takes each individual word or each individual token that it's predicting, and it treats that as kind of its own inference. So the main thing that this enables is you don't have to wait for a big, long inference to complete before you can kind of return the result of your initial inference. So you can see an example illustrated here, but there's no wasted compute because the model is always kind of operating on the optimal number of batched records at any given time, and you get your response back faster. Okay, so that's really cool. We're going to take a segue into Beam model management, and then I promise I will relate the two. So back to Beam. How does Beam generally do model management? So when you think about a distributed Beam runner, you've got a worker VM, and then you've got some number of worker processes spun up. In some cases, you might just have a single worker process. But if you've got multiple cores, especially in Python, it's usually much more efficient to have multiple worker processes available to you. This works really well for small models, because if you've got a small model, your ideal architecture is basically a bunch of parallel I/O model threads, and this maps perfectly onto the Beam architecture. The only change that RunInference makes as it loads models here is that it will share a model across threads within a single process. But it works really poorly for big models. If I have 8 large language models that I'm trying to load into memory, I'm going to get a NUM. There's not a really easy way to work around this if you're just kind of doing things naively. Your options are maybe use a giant machine that has a ton of memory, or operate with a single worker process when you would rather have 8. So your ideal large model configuration looks more like this, where you've got a single model sitting in the middle and a bunch of I/O threads feeding it. You could also imagine maybe you've got a medium-sized model where it's convenient to have 2 copies of the model, but it looks something like this. So how do you map that to this, which is your beam worker topology? And the answer is that you can spin up a dedicated inference process. And Beam makes this really trivial. So you can see this is kind of your normal Beam model handler configuration. The only thing that you need to do to change that and load a single model into centralized memory is introduce this large model equals true flag, and Beam will handle the rest. Under the covers, it's using Python's multiprocessing library to handle all of the requests. You might think that sounds expensive. Almost always, it is outweighed by the input and output to the machine, which is much more expensive in general. But you should try it for your particular use case and make sure that holds up. Okay, so I promised that vLLM would fit in here somehow. So how does vLLM fit in? vLLM is not a model. It's actually a standalone service that you start up. Normally, you spin up your vLLM service, it loads 1 or more models, and then it performs inference. That doesn't really fit in to our traditional model for how Beam handles models, or excuse me, how RunInference handles models specifically. But it does actually map pretty well to this last picture here. What we want is, instead of having a centralized model, we want to have a centralized model service. And beyond that, we ideally want something that, if it falls over, if there's an error or an issue, can self-heal, and the different worker processes can kind of talk to independently. And so that's what we built. We built something called a model manager. So instead of having this central model that you load into memory, you load the model manager, and the model manager is responsible for starting up a vLLM server. It's responsible for talking to the worker processes and informing them how they can talk to that vLLM server. And it's responsible for all of the management of that server. So if something goes down, it can restart it automatically, or it can look at it and say, like, oh, that's an actually fatal error, and we need to garbage collect everything and try on a different worker. So yeah, that's what I just said. The usage is really straightforward. And actually, if you go into the code base, you can look at this, and vLLM, there's no special code in RunInference. It takes advantage of all of the existing stuff, and it just adds this vLLM model handler on top. So to use it, you just need to have some set of prompts as your input P collection. You need to define which model you want vLLM to load, and then you stick it into the middle of your pipeline. And it's that straightforward. So now I'm going to switch to a demo that shows exactly what this looks like in practice. So I kept my Colab instance running with a sleep. So the first thing I'm going to do is, before I even show what it looks like to run vLLM in Beam, I'm going to start up a vLLM server independently so you can see kind of what it looks like to interact with it naively without Beam. So right now, what we're doing is we're spinning up this vLLM server, and we're loading, again, just another kind of small model that can fit into Colab memory. I think it might be a little bit bigger than the other model we loaded because vLLM is memory optimized. In the separate terminal, I'm going to do a couple things. First, I'm just going to get my dependencies in order and install OpenAI and enter a Python shell. And then once this vLLM server finishes spinning up, I will use the OpenAI client to communicate locally. And I need to actually import it first. And we're going to use the OpenAI client to talk to this vLLM server locally. And so you can see it takes a little bit of time because it's downloading the model. So we'll wait on that for a moment. But what we're going to eventually see is that we can feed it completion requests, And you can imagine if there were a bunch of different kind of terminals talking to this endpoint at once, it would do the dynamic batching, continuous batching I described here. And it would work on those all at once. So it's almost done. And then we can send it an example request. Cool. So you can see that this vLLM server has started locally, and we can now talk to it like we would any other kind of model server. So I show this because this is essentially exactly what Beam is eventually doing under the surface. It is going to start a model server just like this, and then all of your Beam worker processes are going to talk to the LLM in more or less this exact same way. They're going to communicate across the process boundary using the OpenAI client, allowing vLLM to do all of the smart vLLM things that it already does. So if I go ahead and I stop the server, we can show what this looks like in Beam. And the cool thing here is it's about the same amount of code, maybe a little bit less even for the vLLM part. So we're going to create our model handler, which loads that exact same model. We'll create some prompts and format the output. And then this is our entire pipeline to run locally with vLLM. It will also take a moment to run, again, because it needs to download the model. But it's doing all of the exact same things that we'd expect from the vLLM server. It's spinning it up in this central process, and we're able to talk to that. While we're waiting for this to run, something I'll point out is that vLLM is a good illustrative example, but this is actually a generalizable problem. There's all sorts of machine learning frameworks which you can run locally, but people normally run as a service, which make it really easy to serve models efficiently in the middle of your pipeline. And this pattern applies to all of them. So this pattern can be easily copied from the vLLM model handler specifically, and be used to run with insert your favorite model serving framework. Okay, there we go. So you can see we gave it this whole set of prompts, and once it downloaded the model, it blazed through them. So you can see, let's pick a random prompt. If we look at emperor penguins are, it completed it with most likely pre-existing predators, which I didn't know. So that's what using vLLM in Beam looks like. So the last thing I'll call out is performance. So when you're using vLLM, and this is like really important to think about, like I ran some benchmarks, and for one pipeline, I saw a 23x reduction in the total number of CPU or GPU core hours used. It varies a ton. We've seen bigger gains, we've seen smaller gains depending on the specific pipeline. But using the model manager, we're able to open up Beam to achieve these really significant performance gains, and you don't really need to change your pipeline to consume it. The only thing you need to do is use a model that vLLM knows kind of how to talk to. So that's my presentation.